Thank you very much for showing up still in respectable numbers. I will start with a quotation of Galileo, I guess in English, or in Italian also, that you certainly heard of before. He said, philosophy is written in this grand book, I mean the universe, which is continually open to our gaze. But it cannot be understood unless you learn to comprehend the language in which it is written. It is written in the language of mathematics. Its characters are circles, triangles, and other geometrical figures without which it cannot humanly be understood. So you are very courageous because here I'm not using mathematics to explain physics. So, but you know the mathematics of this. I mean, it is quantum mechanics, and it is the Hubbard model. And the mathematics that I will explain during this series of lectures will be more about methods. And it will be in the second half of the third course and the second half of the last course. So for today, there will be a little bit of mathematics, but really very, very, very little. Yes, so the statement was that Leonardo said that, again, another great Italian, that you need first to observe, and we agree that this has been the great progress since Aristotle. So let me summarize what we saw last time very briefly. So first, I discussed that the high-temperature superconductors are very correlated. So this was the resistivity as a function of temperature that showed that we go above the Mathieu-Féregal limit. This was X-ray absorption and showing that doping these systems is not like doping a semiconductor. And I talked about RPES, where this is a momentum distribution curve. So we are at the upper quadrant of the Brillouin zone, and red means that the cross-section is very large, and otherwise it's small. So you see, instead of having a Fermi surface that is along this semicircle, pieces of the Fermi surface seem to disappear. So we decided to focus on the one-band Hubbard model that was proposed by Anderson for these systems. Because it has both potential energy, which tends to localize electrons, and kinetic energy. And the phase diagram that we want to explain today, or at least gaze at, to paraphrase Galileo, is this phase diagram. So we have temperature as a function of hole concentration. So 0 means half filling, and P is hole doping. And there's a Néel temperature. I did not discuss this very much, but there's an incommensurate spin density wave here. There is a superconducting transition temperature, a charge density wave, onset, and a crossover temperature, T star, where the magnetic susceptibility starts to fall down, as shown very early on in the game here in Paris. And below, there's a Widom line that I talked a little bit about yesterday, and that I did not put on this plot experimentally. I also pointed out or reminded you that we can get rid of the charge density wave by applying pressure. These are recent experiments published, or not published, appeared on the net last week, where if you apply a large pressure, you see that the superconducting dome is now centered around roughly the same temperature as the, oops, let me go back twice, roughly the same temperature as the charge density wave. And the method that we use, I did not describe in any detail except to say that it will be done in the last lecture. So it's cellular dynamical mean field theory, which is a cluster version of this the single-site dynamical mean field theory that I presume everyone here has heard of before. So another point I made last time is about this phase diagram, where for let's say a three-dimensional system on a square lattice, I plot the temperature as a function of interaction strength U. Sorry, the U disappeared somehow. And the phase diagram is very simple. There is the Néel temperature. And we know that the physics, as we come this way, is Slater. This way is Heisenberg, means here we have localized moments. Here we have a Fermi surface. And to go from one regime to the other, we need to cross a line that is a crossover line. That's the Mott transition. And this, I will come back on that in a few minutes. You see that this normal state is controlled by a first-order transition here that would be there if this anti-Fermi-magnetism was not present. And I did, using these methods, I showed some agreement with the phase diagram of organic superconductors that I will not discuss in this talk. So in cellular dynamical mean field theory, there's an emergent first-order transition away from F-filling. So if I plot temperature as a function of hole concentration, a very rough sketch of the phase diagram is this. And there's a series of questions that are interesting that I will try to give, sort of suggest partial answers to today. So today there will be two parts. The first 45 minutes before the break will be on the normal state, basically focusing on this first order transition where we get signatures of Mott physics away from F-filling. And I will talk also a little bit about superconductivity, but in the second part of the talk after the break, I will try to say what is special about strongly correlated superconductivity and what is the origin of superconductivity, or at least try to get some partial understanding of where superconductivity can come from. So let me begin with something that for about 10 years we know how to explain and we all agree, which is this pseudo gap that's observed in RPES. So I showed it a little bit earlier. If you do just very simple cluster perturbation theory, which is like DMFT, cluster dynamical mean field theory with huge systems but without a bat, then you see these same features. So this is what I call a strong correlation pseudo gap. So in the case of the electron doped superconductors, in the next lectures I will explain a pseudo gap that doesn't need very strong correlation, but here you do. It's different from the Mott gap. Mott gap is local. And even if you dope, it is still there, but away from omega equals 0. Whereas here it's close to the Fermi level, and it's independent of the cluster shape and size, and it's not caused by anti-ferromagnetic long-range order. In fact, it's not very sensitive to band parameters, and it scales like hopping. So it can be seen even with just two-site calculation. So it was done here in Paris, right, a group with Antoine and Michel and Olivier. and you can see that already with two sites, when you underdope sufficiently, you see these pseudo gap. And all groups, whatever the size of the cluster, we all see the same thing. Roughly speaking, the situation is as follows. If you're far from the F-filling, so F-filling is this n equals 1 line, then single-site dynamical mean field theory is correct. In other words, the self-energy does not depend on direction. As you move closer to F-filling, you start to have momentum differentiation. That is, it depends on the direction. And eventually, you can get within this method something that is probably related to the pseudo gap phase. Okay, so let me step back. I start at half filling, and then we'll move to finite filling. So let's recall the Mott transition at half filling. So there, you know, the first calculations were done more than 20 years ago here in single-site dynamical mean field theory. And nowadays we still see this first-order transition in bigger cluster, for example, 4-site clusters. And I don't want to go into the details of this transition. What's important is that it exists and it's seen in all these cluster calculations. So it has to do again with this phase diagram. And the point I want to make is that, again, is that the normal state here is controlled by this first-order transition, even if you don't see it because it's covered by antiferromagnetism. If you were able to remove the antiferromagnetism, you would see this first-order transition. In other words, it's like a mean field theory that is valid down to 0 temperature, but in some state that is not the true ground state for the case I just talked about here. But in the case of the BDT organics that I discussed last time, the antiferromagnetism is so frustrated that in fact you do see this first-order transition come out.
What is the meaning of the point where we have some change of slope in the green line?
Okay, so no, this is just because I'm a bad drawer. Okay, this is PowerPoint, and I'm not very good with PowerPoint. There's nothing. Yes.
With antiferromagnetism, do you still have the Mott insulator transition inside the antiferromagnetic phase?
No. Inside the antiferromagnetic phase, there's a gap here, there's a gap there, so it's a single phase. But as I tried to explain it, it has the same Goldstone mode, the same broken symmetry, yet there are differences. So as soon as you move away from 0 frequency, here you will get Landau damping of the spin waves, here you won't. Here you get some pressure dependence of T and L that is clearly different from here. The normal state here is a metal, here it's an insulator. Even though this is a single phase, there are still differences as soon as you go away from finite frequency, from 0 frequency, I'm sorry, in the nature of the phase, of the excitations, I'm sorry. Okay, more questions? Okay, so dope Mott insulators. So this was looked at more than 10 years ago by the group of Gaby Cotillard in single-site dynamical mean field theory. So it's a little bit complicated here, but let's go slowly. You have temperature, and doping here is a chemical potential. So what I've shown up to now occurs at half filling. So along this line here where I increase U and N equals 1. So I'm half filled. Now, there is a critical point here, the end of this first-order transition, where the compressibility diverges. Now, suppose I stand at this, and this was seen in the organics experimentally in Sherbrooke, and the group here in Paris explained these experiments in terms of this compressibility divergence. Well, in presence of a lattice, it's not a real divergence, but let's say it becomes large. Now, let's look at U relatively large here. So everywhere here, until I hit this line here, or that line, as I change the chemical potential, I stay within the Mott gap, so N equals 1. And then as soon as I cross this line, I go into a finite doping. So I don't go to infinitesimal doping, I go to some finite doping. So there's a first order transition. So there's a hysteresis here. You can see, if I go back, I stay in the metallic phase before I go to the insulating phase. There's a first order transition between an insulator and a finite doping metal. So what happens if you look at clusters now? Okay. If you look at clusters, something we all agree on is that there are some crossovers here. So if you look as a function of temperature, so there's temperature here, doping on this axis. You see n equals 1 is here and it goes down. Here is again the temperature and doping. So this is by the group of Jarrell. This is by the group of Cotillard and Hawley. And the people use different labels, but the point is that there is some region that is more pseudo-gap-like, some region that is more metallic-like, and some strange thing in between. Now, the group of Jarrell even saw a first-order transition in the electron dope case between a metal and an insulator. This was seen also in the electron dope case, again, by a group in Jülich of Leipzig. And in variational Monte Carlo, there's also a first-order transition. I don't go into any details here, I'm sorry, but just to give you overall flavor. First-order transition between an insulator and a metal in the normal state. Okay, so now let's look in more detail at this doping-induced Mott transition. So, yeah.
You mentioned some marginal Fermi liquid phase in Jarrell's
Yeah.
plot. How did they determine that?
They looked at they fitted the imaginary part of they fitted the Matsubara self-energy to what marginal Fermi liquid would predict. So it's a phenomenological fit. Apparently, it works in the range that I indicated.
Was it reproduced by all the group?
Nobody else has looked at that as far as I know. Olivier? No. Yeah. So you're very far from... yeah. So here we look at temperature, interaction strength, that's filling, and then as a function of chemical potential. And what I would say is that what we do, in fact, is that we try to learn the lesson from dynamical mean field theory. What we learn is that in dynamical mean field theory, at filling, is that the first order transition plus its associated critical point governs the finite temperature phase diagram, or the crossovers. So the question is, does the same thing happen at finite doping?
Sorry, how do you know about the critical point? I thought TMFT was really good for local properties, but for some long-range correlations like quantum critical would be still some.
Yeah, well, even if you do just the Ising model in mean field theory, just high school calculation, you will find a critical point. So it's the same type of critical point. It's a mean field critical point. You won't get the right exponents or nothing. But the point is that the first order transition ends at some critical endpoint.
So it's what you mean when the fact that you need both the Mott transition and the critical point? Or did I understand?
No, I'm saying that at half filling, there was a first order transition that ended at a critical point.
Yeah.
And above that critical point, there are lines that continue that describe the crossovers.
Oh, okay, so this is this critical point.
Yeah, no, it's not the same as, I'm not,
Electromagnetic QCP or
no. It's not, it has really to do with local physics.
So it's connected to the ratio
It's in the, yeah, it depends on U over T. I will show you. So, yes, please, Indranil.
I thought that if you look in close vicinity to such a critical point, and if you take into account that there is an underlying lattice, you should be able to see some kind of sound anomaly. So in the cuprates, did anybody see anything like that?
Yeah, there are sound anomalies in cuprates. I'm not... I don't know if they're related to what I'm going to show, but definitely there are, yeah.
the cuprates, the critical point should be so high that nobody has really this no
So, you mean so low?
So
so low in temperature.
Maybe I can make a comment.
Yes.
The insistence in which the critical point we are talking about, which is the critical endpoint of the light, is clearly experimentally outside of the antiferromagnetic phase. Then all the sound anomaly velocities you mentioned have been observed. They've been observed in organics, they've been observed in lieu, and so on. But no, I'm talking about vanadium oxides and organics. There, critical point is not something which is hidden. All sound anomalies are also experimentally accessible. I guess what André-Marie is trying to tell you is that in the cuprates, this critical point hides at low temperature.
Right. And even though it may be hidden by ordered phases, like the superconducting phase and charge density wave, the point is to describe the normal state. It is the most natural way in which it comes out. And if you consider the mud case without doping, that's what Antoine was saying, then in some compounds you do see the first order transition, and you see the sound anomalies. Not in cuprates. Okay, that's what you meant, yes. Yeah, in cuprates, definitely the antiferromagnetism covers this first order transition. Oops. So this is the results of the calculation. Now, yes? No, there are some sound anomalies, but they are not huge. Well, I mean, there's even in Toulouse, they say they found a first order transition also in the sound. But I don't know if it has anything to do with what I'm discussing here. So if you look at the filling as a function of chemical potential, starting from half filling, as you change the chemical potential, let's look at low temperature here. So 1/50, that's these red curves. You see you are in the mud gap, so changing the chemical potential does not change the filling. And then you go into a second order like way into another phase that is compressible. In other words, the ND mu is different from 0. And then you jump to another metallic phase, and there's an hysteresis loop. So it's definitely a first order transition. And these points here are spinodals. In other words, if you can see very clearly that there's a range of doping where there are no solutions at this temperature. So I will come back on this later when we have another view. We look in terms of temperature and doping instead of chemical potential. So to draw the phase diagram, you do many plots like this. Then let's look at the red line here, which corresponds to this temperature 1/50. So when the density is equal to 1, you draw this yellow region, that's the mud insulator. Then you're in this phase that I will characterize later as a pseudo-gap phase. Then you get this first order transition, and again, this metallic phase. And again, there will be a critical point. I mean, this first order transition will end at some point. So, so now if you put all of this together, what you see is that let's look here, for example. So there's this mud phase, pseudo-gap, first order transition. And if you follow the critical point, you see that it is attached to the first order, to the mud transition at half filling. So it's really a continuation at finite doping of this mud transition. And if you look at the critical point, it's this dashed line. So the end of the first order surface is along the dashed line. And you see that it falls very quickly as you increase the value of U. So increasing U this way, temperature this way, and sorry, I should have done that before, and chemical potential this way. I just turned sideways the series of plots that you obtain like this. So with Clausius-Clapeyron, you can find that the underdoped phase has a lower double occupancy, lower entropy, and it's more compressible than an ordinary metal. And I will come back to this point later. So what? Yes? No? Okay. So what happens to the doping, the critical doping as a function of U? Well, it increases. So let me go to the limiting case here. So U equals 12. So at U equals 12, you see, I don't see a first order transition like we saw here. The only thing that's left is that the isotherms, because the red curve is a temperature, the blue curve is some other temperature, 1/25, and you see that these isotherms cross just like they do here, but when they cross, it's due to the first order transition. Here we take this as a signature of the fact that there is some critical point below. What happens at this when these isotherms cross? Well, dN dt at constant mu is 0. So the density does not change. So it's two different isotherms. So density does not change as a function of temperature at fixed chemical potential. By Maxwell, this means the entropy is maximum as a function of chemical potential, is maximum at that point. So this, again, you're going from, it's sort of symptomatic of a critical point, right? When you get to a critical point, you change from one type of phase to another, and then the entropy will want to be large. So we have a finite doping first order transition that's linked to the Mott transition up to, well, I don't know if it's optimal doping. It stops pretty early here. It stops at 10% or so doping. But that's for the model where there's no T prime. And the transition is between a correlated metal and a pseudo gap. So let me start again. This is doping, U. As I increase U, I hit at half filling, so no doping. I hit the Mott transition. So here I have an insulator, here I have a metal. If I dope, I go in a second order way in this pseudo gap phase. I have a first order transition and then the correlated metal. So that's the phase diagram I showed. So let's flip now and go into the doping instead of chemical potential. So I have temperature as a function of doping. And as I said, there is a region where there are no solutions. So there's no, it's really, you have the spinodals that are here, and here it's sort of, to have a density in between, you need to mix the phases. And what I showed is that it ends at the finite temperature critical point. Now what happens above this transition is the rest of this talk almost. This is the Widom line. So again, for T prime equal to 0. So what is the Widom line? I mentioned already in the first talk, but let me repeat again. Let's look at just some liquid-gas transition. So I have pressure, temperature, a first-order line between gas and liquid that ends at a critical point. So you can go continuously from gas to liquid across this point, but the point is that there is a line that is not a first-order transition, but some sort of crossover line where things change very quickly. So if you look as a function of, if you look at various thermodynamic quantities, you will see that you have maxima along this line. And the crossovers are not necessarily exactly at the same point, depending on the physical quantity you look at, but asymptotically, as you get to the critical point, they all merge to a single line. That's called the Widom line. And not only the thermodynamics, but the dynamics is also doing something. In other words, here, the viscosity would be more gas-like. Here, it would be more liquid-like. So in the results I'm going to show, I'm going to focus on U equals 6.2, which is small for the cuprates, but has the advantage that we can see the first-order transition in the calculations. Otherwise, the sign problem prevents you to go to low enough temperature. So let's hunt for the first-order, or the Widom line. So at high temperature, I plot a thermodynamic quantity, the compressibility, the n d mu, divided by n squared, as a function of mu. At high temperature is the black line. you see nothing very interesting. But now, as I decrease the temperature, I start to see maxima. And if you plot the locus of these maxima, that's what we will call the Widom line. And as you get closer and closer to the critical point, you see this is a semi-log plot. You see the blue peak is quite large here as a function of chemical potential. So there are many, many crossovers along this line, and I would prefer to show them in the doping plane instead of chemical potential. So here, as I show the results, I will show some comparison with the cuprates. And the caveats are that U is not really large enough and that T prime is 0. So for the cuprates, you would need T prime and you would need U to be larger. Are there questions while I try to drink? Okay. So let's start with the density of states. So you will see this plot all the time. So temperature, doping, the first order transition, and the Widom line was the red points here. So now if you look as a function of temperature at 2% doping, so you take 2% doping and you decrease temperature, you go like this, you see that at high temperature, this is the black line, pretty flat, and as I lower the temperature, you get a first order, a dip that's called the pseudo gap. And if you plot the value of the density of states at 0 frequency as a function of temperature, there's an inflection point that we put on this plot, and it is the green line, the green points. If you look at the experiments, this is not a really very underdope system, so it's not as asymmetrical as this one. But the point is that if the high temperatures are along this way, these are density of states for various temperatures. They are shifted so they don't all overlap like we did here. The TC is the red curve, and all the other density of states are there. And the point is that the pseudo gap fills in instead of closing, and this is what we see here qualitatively.
Just one slide. Yeah, no, this one. If I had to put the antiferromagnetism on the left figure,
yeah, it would cover this because T prime is 0. So,
this is also far from cuprates, the Widom line.
yeah, so in the same way that the single-site dynamical mean field theory done at T prime equals 0 told us something about frustrated frustrated organics. Here I assume that this will tell us something about the cuprates that have some T prime that's frustrated. But you cannot do the calculation with T prime very large yet because of the sign problem. So if you look,
If you start putting numbers, the Optic being like, I don't know, 2000 Kelvin or something like this, this critical endpoint, which is basically Optic over 50.
well, you can see here the Kelvin scale.
It's well,
Yeah, it's too big, definitely. The critical temperature would have been observed if it was as high as here. Pardon me? This is U equals 6.2. This goes down, yeah. So what about the density of states again? But now we take temperature 1 over 25 and we cross like this. So we change the doping. So at that filling, there's some mud insulator. And if you dope just a little bit here, you see this red curve. You get 1% doping is very, very asymmetrical.
Sorry, sorry again. It's with T prime equals 0, but it's a cluster DMFT.
Yeah.
It's a big cluster, or?
It's always, like I said last time, I should have repeated, it's always this 4-side cluster.
So you can see with this cluster that the gap is the antimodal, so the gap is in the antimodal direction.
Well, I showed you the pseudo gap RPS, and even with two sites, you can see that it's at the antinodal point. That's the sort of the easiest part of the game. It's known for a very long time. It works very well. Yeah. Okay, so if you see experiments have also very asymmetrical curve, and it's easy to understand. It's easier to remove electron than to add electrons. Oops, I have to speed up. If you look at the spin susceptibility, it has an inflection point that again falls on this line, and there's also a maximum, and these are data on the cuprates that show this, and this is the comment that Henri wrote, that in reality the signature in the night shift or the uniform susceptibility is very broad. So you should identify T star as when this starts to fall. And indeed, we have two crossover lines. Oui? That's a night shift. So it's a uniform spin susceptibility. Yes. So in reality, in the cluster, it's not Q equals 0. It's sort of a patch near Q equals 0. It's the cluster. Yeah.
So André-Marie, just to compute chi of T uniform, how is the calculation done? You put the uniform field?
No. We just compute the spin-spin correlation function on the cluster, exactly.
But then you just have local and nearest neighbors. And perhaps
Well, it's Q. You take there are 4 wave vectors. One of them is 0. You take 0, so that it is really an average. It should be thought of as an average around Q equals 0. Again, it's only qualitative. One could compute the lattice using the vertex. Yes, that's not what is done here, but the results are similar if you do the full calculation. Although there's a long time I've looked at the results, but I think they're pretty similar.
And so the onset of the drop of chi occurs at a higher temperature
Than the inflection point. Yeah, higher temperature than the Widom line. So more specifically, if you look at the magenta points here, this is where it starts to fall. That's T star. And this is the Widom line. That's where is the inflection point. Now there's another line that I draw here, which is the C-axis resistivity. So if you look at the forget about the blue region here. If you look above the first order transition, you see that it's rather monotonic, and this is what the C-axis resistivity is on this axis here. This is temperature, and the same thing as here. C-axis as a function of temperature, and you see for large doping it is monotonic. If you go at small doping, then it goes up, and that's this curve here. And the point is that even if you're past this first order transition, you see that it keeps going on. And there's been detailed studies here in Paris in single site dynamical mean field theory. This was known for a long time, but it was systematized here that you cross the Mathieu-Regel limit without any problem. So within dynamical mean field theory, the Mathieu-Regel limit is no objection. What is the physics of getting this pseudo gap? Well, we can sample. We have 256 plaquette states, and we can sample them. And what you find is that the probability that the plaquette will be in the singlet state, which is resonating like this, is, for example, take the green curve here, which is 2% doping, becomes like 60% of the probability. So you really, it's the singlet formation is what's reflected in this pseudo gap, and the inflection point again falls along this line. So the pseudo gap is along appears along the Widom line. In summary, we have signatures of mud physics that extend way beyond the half filling. The pseudo gap is a phase here, although you have to be careful. It's a phase like the liquid-gas transition. So in this region, it's just a crossover. The pseudo-gap T star is controlled by the Widom line and its precursor. There's a high compressibility, that's what that I showed, that may be related to stripes. Yes? Yes? Yeah, they're very close. They're within the error bars, but they're not exactly parallel in this. So if you want, I would say that this first-order transition, in the same way that at half filling, the first-order transition was an organizing principle for the crossovers at high temperature, it's the same thing here. So we have T star, T Widom, and this is where the T Widom is where is the inflection point in the density of states or in the spin susceptibility. This is where there's a compressibility maximum. I will talk now about pneumaticity or anisotropy.
So before you go here you show a plot where T star is not exactly T Widom.
No, it's definitely not the same.
Oh, okay. So good to know.
So what you call T star is the onset.
The T star is the onset here. This is where this was what was pointed out by Henri. The T star usually people define as where the night shift starts to fall. And what I call the Widom line is where is the inflection point. And so there are two lines, definitely. Oops, sorry, I'm going backwards. It won't end soon.
But what you observe is that the line which is actually controlled by the critical endpoint is the one that corresponds to the inflection point of essentially all quantities.
Yes.
Not to the onset.
No. Right. So as I said, so what happens to anisotropy that's often observed in these compounds? So these are results of Mélis and Olivier. I tried to catch his attention here. So these are your results where you show that there's no spontaneous tendency to pneumaticity in a tetragonal crystal, even in big crystals. And we looked at the same for smaller plaquettes, and we get the same results. On the other hand, if you look at yttrium barium copper oxide, it is already tetragonal, orthorhombic, I'm sorry. So what happens if you work in an orthorhombic crystal? This is the ratio between the conductivity along, it's the anisotropy ratio. You take the conductivity along X minus the conductivity along Y, and then you divide by the average. And in the presence of a small orthorhombic distortion. So the way you put the orthorhombicity is just that you favor hopping along one direction a little bit more than the other direction. And here it's only a 4% effect, it's very small. So if you take U equals 4, which is below the Mott transition, you get these magenta points. There's a small bump here because of Van Hove physics. So you see as a function of filling, F filling is here. Nothing happens if you're below the Mott transition. If you're above the Mott transition, for example, U equals 6, these are the blue points. You see that when you get near this 4 or 5% doping that I was talking about earlier, there's a big jump in the anisotropy. And if you go to U equals 12, it starts to occur earlier, consistent with the fact that the first order transition moves as you increase U, I'm sorry. And the effect is not as big, but clearly there's a large anisotropy in the pseudo-gap region. And you can see this by looking at momentum distribution curves. So the anisotropy is really in the scattering rate. You see a piece of the Fermi surface here has disappeared, and it's sort of consistent with what is seen experimentally. Although experimentally there are chains, so the story is not perfect. Now this calculation was done at finite temperature, and you see this onset of anisotropy at the temperature that is near T star. So what they plot here is temperature as a function of doping, and when it's yellow it means large anisotropy, and black means no anisotropy, and the anisotropy starts to appear around T star. Yes, Catherine?
So if you remove this 4% of orthorhomicity, you observe nothing.
That's right. No anisotropy.
So do you push it to say like some more tetravalent compounds like mercury?
So the prediction here is that in mercury you will not see this. Right. So in other words, it is not the electronic. It's not the Hubbard model that drives the nematicity here. It's just that once it's orthorhombic, if you are in this pseudo-gap regime, then the scattering rate becomes very sensitive to direction, and then you have a large anisotropy.
Perhaps an even stronger prediction is that if you take mercury 1201,
Yes.
you will see nothing.
Yes.
If you put a small uniaxial pressure,
Yes.
you will see a big response.
Yes.
The susceptibility is large, but that's diverse. The susceptibility to authenticity is getting larger.
Well, but you show that it is zero as far if you look. Pardon me? Yeah, this is lifetime. We're not talking about the thermodynamic susceptibility. But the response here is in transport. But certainly there will be some charge effect also. But actually this we have not calculated yet.
So the susceptibility is not increasing at all if you don't put a residual 4% orthorhomicity.
Right. If you look at thermodynamic quantity, in other words, you look at correlation between fluctuations along X and fluctuations along Y. If there was some tendency, some thermodynamic tendency to nematicity, there would be a correlation that would eventually diverge. But it does not. In fact, it is zero.
Well, in STM, it's not really thermodynamic. In STM, as far as I remember, what this is that the nematicity as function of frequency is correlated with the pseudo-gap.
Yes, we see exactly the same.
So it's not thermodynamic. It's very excited, but it's a correlation to the pseudo-gap.
Yeah. And so here we see, that's what we see. I mean, that you will see this anisotropic transport once you have some anisotropy, orthorhombic distortion. Pardon me? Yeah, it could be that yes, but once it's orthorhombic, it can certainly order. I mean, there's no reason not to do it.
Well, if it's an oxygen ordering, then it will be some D-wave character to
Well, here the imaginary part of the self-energy has a small D-wave character, right? Because it's larger here and smaller there. But it's not the same as saying that there's a susceptibility that is large, or even that the real part has the same thing, because the real part integrates over frequency. Okay, so now we see the pseudo gap is a crossover or a phase transition, depending on which temperature you look at. The relation between charge density wave and pseudo gap, well, the charge density wave has some finite wave vector. Here we looked. There's some large susceptibility at q equals 0, but not at some finite wave vector. So it's tempting, but there's no. I mean, I don't have anything to say about the charge density wave. Why is it peak at 12%? Well, we saw in this calculation that 12% or something like that is something that comes out naturally as u increases. But again, I don't claim it explains the CDW.
Sorry, so can you tell more, because I have no clue why you pick at 12%. So can you give me what's your view
Well,
Why should it peak at 12%?
I don't know, but look at this. I mean, the point is that the signature of the mode transition doesn't seem to extend, I mean, really very, very far. But
The clear experiment is 12% for all the compounds, roughly, or something.
yeah.
So
So if U is in if U is in this range, you know 10, and you add the effect of T prime. We know that T prime moves this line this way, but I would be surprised that that T prime is 0.3. It can move by 30%, but I would be surprised it can. But I would be surprised if it moved it all the way to 25% or 20%, right?
no, this I understand. But when we discuss, for example, with the experimentalist friend, they tell you it's between 11 and 13% for all compounds.
Yeah.
It's extremely precise.
Yeah.
So it was calling more some kind of, I don't know, symmetry argument or...
Who understands that today?
No, I don't. I know. So, no, but okay, it just
So here it's just a numerical statement.
okay.
Yeah. So okay, I talked about nematicity. It's definitely not driven by the interactions, but if there's some orthorhombicity, what we call it dynamical electronic nematicity, because it shows up in transport very clearly. Okay, so now we are the question: why is it superconducting? Why would the dome be around this transition? So I'm lagging behind. There are lots of questions, so that's very good. So I'm going to postpone this. Yes.
Are there any DCA calculation that was shown in first order transition? To my knowledge, some time ago there was no clear signature like in the field.
That's right.
We don't know yet.
The question is, has the first order transition been seen in DCA? And the answer is not yet. It doesn't mean it's there. If you don't see something.
We will know shortly.
Pardon me?
Somebody says that we will know it shortly.
We will know it shortly. Okay. Well, what I can tell you is that these calculations we did in DCA too.
Yes. Yeah, that's the reason I'm asking, because
And in DCA you see the same thing, except that it occurs before it does here. So, but qualitatively it's exactly the same results. But this is not. I mean, this is a little bit different from the first. It looks like the first order transition because you see there's a region here between the green points where the reason there are no points is that it did not converge. So we assume it's the first order transition, but it's not a proof like it was. It's not a solid proof like it was in the Monte Carlo calculations. Yeah. Yeah. Well, you're an author on this paper, so it's your fault if you don't like it. Yeah, absolutely. Yeah, I agree. That's exactly what I said. Yeah, that's exactly what I said. Yeah, it's tempting, but it's not reliable enough. In fact, there's this. Yeah. So with Monte Carlo, we saw the first order transition. Here it's very close to a sector change. So, but on the other end, in the case where they did with finite T prime electron dope, then there's no sector change. So. Okay, so D-wave superconductivity, I won't go into the experimental proofs. By now it's been established for more than 20 years. In the case of theory, there are a lot of approaches, functional RG, normalized mean field, slave particles, variational approaches, and within the type of methods I'm discussing here, so dynamical cluster approximation calculations by the group of Jarrell looked at the size dependence over a broad range of size, and they see that the inverse D-wave susceptibility as a function of temperature does vanish. In other words, its inverse diverges at a finite temperature. And again, I hope, Marcello, you like this plot, because So this is the phase diagram as a function of filling found by these cluster methods at 0 temperature. And the only thing I want to point out is that you see D-wave superconductivity, you see antiferromagnetism, and they compete, and there's some small coexistence region. Okay, so I'm already very late, so I will stop here for the break, and I will discuss everything about superconductivity in the second talk. And obviously, I will skip a lot of things. So we are here now.